Hello everyone, hope you're doing well. Before we start the second phase, do you have any questions regarding last time? Something that you want to come back to or that wasn't clear? Yeah. Anyone has tried the exercises a bit? Some? Yeah? Cool. Did it work? Was it hard? Ish. We can discuss them if you want some, you know.
Is there any good documentation for Casadic? Because
good question. I would say no, to be honest. There are lots of examples. So if that's the bottleneck for you, we can try to look at the codes together, and I can give you some.
I figured it out. It just took time to find the function that did what you actually
wanted. Yeah, I agree. Yeah, that's one of the difficulties with it. There are actually new layers now on Casadi that allow you to write your problem more like you would do in YALMIP, where you just declare constraints, like just declare the symbolic variables and then assemble the constraints a bit. At a higher level than what you do in so we could look at that as well. I did not convert exercises to this version yet, so yeah, but there is a bit of a steep slope to learn this thing. Yeah.
Is there a auto-generated documentation for?
There is documentation, but it's just doesn't seem like it's enough information to be able to know what the actual functions do. So it just usually just says input and output, and then you have to figure out what the function actually does.
But I can share the codes that solve the exercises, and you can also look at them. That's typically the best, to just look at how people would do it. And yeah.
Do you have solutions for the non-programming tasks as well?
The NLP? Yeah, I must have. Yeah, I could put them online.
That would be good.
Yeah. Yeah. I could do that. Yeah. Yeah, and if you have any any concern, we can just discuss them. We have enough time for that. All right. So what we did so far was mostly to talk about how we solve NLPs, and that's a really important part of numerical optimal control, because you basically always end up doing that, regardless of more or less regardless of what you use as a technique to discretize your problem. So there was quite a bit of talk around not really optimal control related stuff, but and we'll discuss a bit more later on how you solve NLPs, because we basically saw the KKT conditions, Newton, and then SQP. And in the map, you've seen that there are other blocks that we should also talk about. But before going there, I wanted to, at some point, talk about really optimal control and how you actually solve these problems, or how at least one way of solving these problems, for you to dive into this question without so much more delay. So I will start today with talking about shooting methods. That's one of the big class of approach for solving optimal control problems. So if we go back to the map, if you remember these things, so we have discussed essentially around these questions inside this box. So the KKT conditions, that's essentially the set of conditions you need to solve your NLP. We discussed Newton as a way of solving algebraic equations, and we then finished with SQP essentially, which is one approach to solve NLP. So we work in that box. And if you remember, one of the issues was this disjunction condition, like this mu times h equals 0. If you remember, that's creating this corner in the algebraic conditions. And what SQP does, and that's the big problem for Newton when you want to solve the KKT conditions. What SQP does with that is kind of moving this problem further down in the layer. So it's moving the problem of this corner down inside QP solvers. So SQP is calling QP solvers a number of times, and this corner problem is hidden inside these boxes. So we'll also look at how these things handle this corner. The other way of handling the corner is this thing that we'll also talk about later. Essentially, we've been discussing a lot around these things. We'll discuss a bit more later. But now what I want to discuss are these boxes here, the shooting methods, single and multiple shooting. And that's really about going from an OCP. So remember, that's essentially your basic optimal control problem with differential equations and integral cost functions and so on. And you want to take that thing and create an NLP that is a good approximation of your problem. So you have these three paths to do that. There are some more, but I would say these ones are the most used by people and the most successful typically. So yeah, we'll discuss these two boxes. So how to go from an OCP to an NLP. Any question on that before? Yeah. Okay. So I'll talk about this. That's the menu today. I'll start with a single shooting approach. That's kind of the most obvious thing you can do for doing this conversion from OCP to NLPs. And I want to show you a bit what happens there. And then we'll talk about multiple shooting, and then I'll discuss a bit more about how the NLP looks like when you use these discretization approaches. Yeah. So here is essentially what single shooting would be doing. So that's your optimal control problem. So some differential equation. For now, we talk about classic ODEs, some cost functions, some inequality constraints, and typically some boundary condition. Often it's at the initial conditions. It may be somewhere else, but we'll mostly stick to that. In the context of numerical optimal control, where the boundary conditions are is not very important. It will not make much of a difference in the method, so that's not something to worry about. So what you would want to do, the first thing that you cannot really deal with in problems like this is the fact that your input is, or this variable that you want to optimize over the control profile U, that's infinite dimensional if you want. It's a function in time. So we don't know how to describe this in the computer. So you need to discretize that thing for sure. One thing that is typically done in numerical optimal control, that's not, you don't have to do it that way, but that's very common, is simply to use piecewise constant inputs, right? So essentially create a time grid that spans your control horizon from 0 to final time, and you will just basically say, let's say that the input is constant over these different intervals, and now I've converted this infinite dimension object into an object in Rn, say. So I can just adjust each of these levels, and that's a vector of numbers, and this now is my set of decision variables. So you don't need to do it that way. You can, of course, for example, describe your U by a curve that is parameterized. You could use polynomials and so on and so forth. We will see in the following that, however, there is something important in the way you discretize this U, in the sense that, and I'll try to explain that more later, but preempting a bit what's going to happen, it's very important that the way you parameterize your U will make the parameterization local in some ways. And by that I mean that if you have parameters that describe the U in some parts of the horizon, these parameters should only impact a part of the horizon and not impact over there, for example. So that's the case here. If you move the parameter describing this level here, that's not going to change the rest. But if you're, for example, building a polynomial that would describe the U throughout your horizon, if you were moving one of the parameters in the polynomial, the whole thing would move around. I will see what, I'll try to tell you what happens if you do that later, but essentially it will destroy the structure of your problem and make it harder to solve for the computer. So if you want to parameterize the U with something finer than a piecewise constant, use, for example, piecewise polynomials, right? So you could have a polynomial in here that describes the u in this time interval, and another one here, and each of them described by parameters. So you can do lots of things around that, but most often in practice, people just do it piecewise constant and use a quite refined time grid so that the signal for the system looks kind of as if it was continuous. So with this control input, in principle, you could simulate your system, so the dynamics, starting from the initial condition x0. You just apply the input to the ODE, simulate, and you collect your complete trajectory x at all t. So you could see something that is starting at x0, simulate that, you end up here at xtf. So that's the description of your trajectories. So you could really imagine that essentially this x dot, and by that I mean the complete profile of states. You could see that as a function of your input sequence, this u0 to un minus 1. So you have n of these discrete inputs of also the initial conditions, of course, and of the different times. So you can think of a function here that takes the discrete inputs, the w's, initial conditions, time, and maps all these things into this complete profile, right? And that would be essentially a simulation routine that would do that. So of course, you cannot typically generate this, you cannot write this function on pen and paper for most systems. If your ODE is nonlinear, you may not be able to write the function that delivers this x of t, but what you can do is build this in the computer. You just simulate the system, right? And then you actually don't have the full x of t, you have like a lot of points along this trajectory that describe this simulation fairly accurately. Okay with that? Yeah, so you can, this function is a computer code, but you should look at it from a theoretical point of view as a mathematical function. So yeah, computer codes can be mathematical functions. That's essentially the point. And it has some properties like the partial derivative of this function with respect to time is f, of course, because essentially describing the dynamics. And at time 0, the function should return the initial conditions. So that's hopefully kind of obvious. But if you, yeah.
So if you use single shooting, would each state vector at each time step not be a part of the decision space?
No, so exactly. So I'm going there. So in some sense, if you look at the states over time as this function here, you don't really need to keep your state as decision variables. They are functions of the u's. So you could think of your u's as the decision variables, and then this function will just explain or connect the inputs to these states. So in that sense, you could eliminate them. So that's where I'm going. Maybe if I show the NLP you get from that, it's a bit more clear. So essentially, now that if I am equipped with that function, I can essentially replace every of my x dots by that function itself, right? So I could evaluate the cost based on this simulation. Maybe if it's an integral of x squared or something, I just process that. And in that sense, this cost function becomes a function of w and x0 that is fixed anyway. So I could look at my function phi as a function of w alone, right? Same for the inequality constraints. I just plug my simulation in these constraints here. If I had some terminal conditions, for example, here, that would be the case. I would impose that my simulation at the end meets some conditions. And maybe one small technical detail. This is a very nasty thing to impose. Imposing that h is negative at all time. It's a semi-infinite constraint. So it's in the computer. I would not know how to do that, because you essentially have to say that's an object at infinitely many points, if you want, is negative, right? So this is typically replaced by imposing the constraints on a set of points. You see that? Yeah. And most often we use the time grids to impose this inequality constraint. So on each of these points, we want H to hold using the simulation function. Yeah, the WK, that would be the U of t on the different times, but that's essentially these constants. So that would be the kth entry of W and at time tk. So yeah, you impose the inequality constraints on these points. Of course, it does not give you any guarantee of what happens in between. So it's very possible that if you impose that, the actual trajectory is violating the constraints in between 2 points, right? Does it make sense? Yeah. And that's a problem that people are fully aware of when you do numerical control, optimal control. And there are some ways of solving that in some specific cases. Most often what people do is just use a dense enough time grid and typically a little bit of back off on the constraint so that your solution is in the feasible domain at all time. Okay with that picture? Yeah. So when you do that, essentially discretize the input and keep only the inputs as decision variables. And essentially here I flushed out these dynamics because they are basically handled inside the simulation. I don't have the OD anymore, it's kind of hidden in that function. So that's a single shooting approach to solving an optimal control problem. Okay, so let's try that. And we could do it, for example, on a very, very classic example, swinging up the pendulum. So it's like, let's go. So essentially you have, I mean, it's very classic. You have a cart and you move the cart so that you bring the pendulum up and then keep it up. So you want to start from a given position, do something, and in the same position, pendulum stopped, cart stopped. Yeah, so you can see the picture here. And you want to do this by minimizing, or you want to minimize the usage of the input while you do that. And U would be like the force on the cart, typically. So here is my OCP. Here I already discretized the inputs as piecewise constant, but I still have a continuous optimal control problem. I still have X as a continuous trajectory in time. So I still have an OD in here. I bound my inputs and I impose some initial conditions. That's pendulum down, everything stopped, and terminal conditions, everything at 0 means pendulum up and the cart is stopped and the pendulum is stopped. So the 4 states would be position velocities of the carts and of the angle. Okay with that? Mm-hmm. Okay, so again, you have essentially need to create an integration function or an integrator, essentially a simulation code that would provide the state x of t at any time t as a function of the sequence of inputs, initial conditions, and time t. And maybe it's obvious, but it's not maybe not obvious for everyone. Even though this thing here is a computer code, you should think of it as a mathematical function. So, for example, in principle, it would be completely okay to ask what is the derivative of this function with respect to the inputs, right? And we're essentially talking about differentiating a computer code. And that is possible under some conditions. You have actually an entire field of research called algorithmic differentiation, which deals with that question, differentiating computer codes. And we'll see that, of course, this thing here plays an important role when you want to solve the NLP. So the sensitivities of the functions you have inside your problem. That's because when you apply Newton or an SQP method, you end up differentiating all your constraints and your functions. So you need to be able to do that. Okay, so if you convert this OCP into an NLP using single shooting, so you don't need to touch the cost function, it's already in the right form. This is fine, it's just a constraint on the inputs, it's already discretized. But then you have this integration function that flushes out the dynamics, and the only place where you need it really is on this terminal constraint. So you want the simulation to terminate at 0 essentially. So you want your integration function, depending on your inputs and initial conditions, at final time to be 0. Okay, so it's a constraint on your essentially on your decision variables. You need to select the U's such that this condition hold, and that will be actually a constraint in R4. Right, I have 4 dimensions that must be at 0 because I have 4 states. Make sense? Okay, so let's try that. And we saw SQP last time, so there should be no mystery here. So here I report my inputs, and these are my decision variables. These are the states obtained from the simulation, but they are not part of my problem of my NLP. And so that's my initial guess. I'll just say I have no idea what I should be doing with this system, so I will just say I don't know, just I put 0. I don't know what I should be doing, tell me. And this constraint here, that's the terminal constraint. On the graphs you see that's the circle here. So essentially the simulations must hit the circle on these 4 plots, right? So it's 4 constraints that you must enforce. And so of course, if the pendulum is down and I don't apply any inputs, the trajectories are flat, right? It's just staying there. And all the constraints are met apart from the angle. So this thing here should be reshaped to meet the angle equals 0, right? So the SQP will have to work on that. Okay, so if we unroll the story, so that's the first iteration of SQP. It's doing something, kind of oscillating the pendulum. You see we're doing something with the with terminal condition. Second iteration, third, fourth. It's kind of moving around. Now it's kind of figuring out something a little bit. You see that kind of oscillations in the inputs. That's what you expect the solution should look like. And after 17 iterations, we start to hit the constraint, and then the SQP works a bit more to minimize the cost function as well. Okay with that? Maybe some remarks. You see that the trajectories on X dot, for example, they are a little bit like they seem to have some corners. That's of course because so U is attacking the system at the level of X dot dot. So if U is piecewise constant, then X dot would be kind of the integration of that and has this discontinuity in the derivatives, right? Because X dot dot would be discontinuous. So you can see this effect here on the trajectories on the simulations, a little bit here as well. Here that's more or less smooth. Yeah. Any question on that?
The final time, if that's not fixed, because I assume you set it to 2 seconds now.
Yeah, here it's fixed. Yeah.
How much harder does the problem become then?
If you have an open final time.
Yeah.
So, okay, that's an excellent question, because people often are a bit struggling with this problem. So first, if you have an open final time problem, you should do a time reformulation. We can discuss that a bit more offline, but what you do in that context is that you reformulate your ODE by essentially introducing a parameter here, right, that would actually create an open final time. So it's not obvious at first glance, but if you have this parameter, and that's part of your decision variables, that actually allows your NLP to change the final time. It's doing that by kind of contracting or expanding the time on the dynamics. So if tau is large, then it's like accelerating the system, and it's like contracting the final time. And if tau is low, then it's the other way around. And then you impose like the time inside your solver then is fixed. So the computer time, if you want. So if you do that, that's the timer formulation. That's what you should be doing to handle the open time problem. But this is much harder to solve, yes. And one way of understanding that is imagine that you have actually a linear system. In principle, that would be very easy to solve if it's linear. The OCP would be convex and the NLP as well. If you multiply that by tau, and that's a decision variable, that's nonlinear. So you made a convex problem non-convex. Having said that, people do that a lot and solve successfully this kind of problem. So it's a matter of giving good initial guesses, and it's a bit the art of solving these problems efficiently. There are lots of tricks that you can use. All right. Okay. So the picture looks good. It seems fine. And the swing up is not a trivial problem, so it's working well. However, this is hiding the fact that single shooting is, in most cases, not the best way of solving an OCP. So that's really not the end of the story. And let's put it that way. I needed 20 iterations to get the solution. That's actually a lot. We could be much faster in converging to the solution. And more generally speaking, solving NLPs using single shooting can be fairly challenging. So it's already about 40 years ago that people figured out that that's not the best way of approaching the problems and invented other techniques. So why is it not such a great idea to use single shooting? That's essentially because of this observation here. So we get back to this integration function of the simulation of your ODE. So really this thing mapping the inputs, initial conditions, and time into the profile or the trajectories of your states. The problem is that on many systems or models or ODEs, this function f, this simulation, becomes highly nonlinear for large T. So as you unroll your time, the relationship between these things here and where x ends up becomes a lot more and more nonlinear. If you're not convinced about that, I can give you an example. Here is a simple ODE, 3 equations. They're actually not very difficult. You only have some bilinear terms like x times u and x times z, x, y. But the rest is basically linear. So it's not a nasty system per se. So I have 3 states and I have some input u in that system. And what I want to show you, I need to explain a bit this graph, I guess, so to really get the picture. So I'm simulating this system over some time. So here from 0 to 0.25, I have fixed initial conditions. And what I'm going to do, I'm going to take a fixed input u and vary it between these numbers, 20 to 35. So this graph would essentially report where the 3 states, x, y, and z, end up at time 0.25 using different inputs in the system and for fixed initial conditions. Is that clear? Yeah. Okay, so that's the situation for t equal 0.25. So you can pretty much see that the 3 states are kind of affine in input or close to that. I mean, they are not exactly lines, but They are slightly curved, but you see that the situation is not bad at all. For example, if I was to linearize that function at some point here, my linearization would be valid for a pretty large set of inputs, right? So if I were using like Newton-like techniques that rely on linearizations of the functions in the problem to find its way around the optimization, this would be good news, right? If I linearize on a point, I have a pretty good model of what's happening in the neighborhood. Okay, but that's for time 0.25. What happens now if I increase this time? So I simulate for a longer time and see how changing the input impacts where the state ends at different times. So that's 0.45. It's becoming more nonlinear. I mean, you see this thing here. That's not that great, but it's still not crazy. Can crank up 65, 85. It's not dramatic. 1 second, it's getting a little bit harsh around here. 125, it's getting quite nasty. You see these big swings here and here. So now if you were to linearize, for example here, the linearization would be valid on a very short span of inputs, right? Same here, you have this very strong changes in these functions. 145, that's getting really bad, right? Look at this thing here. If you try to linearize the function around here, the linearization would be valid only on a very, very short interval. And that's 5 seconds, right? So try to linearize this, you will not get anything useful, right? Okay. So essentially, this kind of simple observation is basically destroying the idea of signal shooting. Because think of, if you had a terminal condition, I want these 3 states at 5 seconds to meet some target. You ask your SQP to find its way in this mess. This is not going to happen. It will basically not be able to find the solution unless you start the SQP like almost at the solution. Like the region of convergence would be extremely small. Does that make sense? Do you know? I put the notes online, so if you read them, don't answer. But do you know what this system is?
Chaotic?
Yeah, that's true. You know what's the name of these equations? Yeah, it's actually a very famous system. Essentially, these 3 equations destroyed our hopes of having long-term weather predictions. So the story behind this, it was in the 50s, I believe. There was a computer scientist at IBM who took the equations of flows in the air mass, and they were like struggling with weather forecast. It was like, let's try to simplify these equations to death. Ended up with these 3 equations. I was like, so is there something wrong with these equations at first? And well, yes, there is something wrong. It's indeed chaotic, and they have these trajectories. That's a famous picture in mathematics. It's the Lorentz attractor. So what happens there is that if you change a tiny bit your initial conditions or anything in the system, the states will just land on a completely different place in the long run. It's not that the trajectories are unstable, it's just that they are chaotic. So you have this kind of features. Okay with that? Okay, so the moral of this story is actually, if you do optimal control, you should not simulate nonlinear / unstable dynamics for a long time. You will often get this effect. It's usually not as dramatic as this one or this example, but you are creating a very nonlinear problem for which Newton will have problems with. Okay. Now, of course, this advice is a bit nonsensical in some ways. I mean, if I have an imposed horizon, like for example 5 seconds on my system, how can I not simulate for 5 seconds and still work with that system or that problem. And people have found the answer to that. I think it was in '84. The paper, first paper on this thing was proposed, and that's gonna be multiple shooting. Before going there, I can just show you a little bit of mathematics around this problem, and I'll not go into all the details, but that's in the slides, and you can look at this if you're interested. So. If you take this statement that the simulation tends to become nonlinear for large time, and you could have the converse statement. So, if I simulate for a long time, I tend to make my simulation very nonlinear. If I simulate for a very short time, will I be guaranteed that my simulation is fairly linear? I.e., this picture I have here. If I simulate for a short time, my functions are kind of linear, or close to that. Is that always true? And it turns out that you can actually show that if you simulate for a very short time, the simulation will tend to become linear in the parameters. So I'll just show you a tiny bit the math you can use to show that. So we can just discuss dynamics without the inputs, just to make it simple, and then you can imagine a simulation function. So that's something that maps initial conditions x and time to the trajectories. This kind of view does not preclude having inputs. You can always look at the inputs as an extra state in the system that has zero dynamics. So when you need to analyze systems and you want to get rid of the inputs for notation reasons, you can always use this kind of argument. So how could you measure nonlinearity in your simulation function? So essentially how nonlinear in X, the initial conditions, would be my simulation. You could do something like this, for example. And that's actually, if you go back to your Newton convergence propositions, you would have things that look like this. So basically, how much is the Jacobian of my function changing with the initial conditions? It's kind of, at least for linear systems or affine system, is fairly obvious. If f was affine in X, then this del f, del x, del f, del y, so basically the Jacobian of the simulation at different initial conditions, that will be constant. That will be a. So you'll be doing a minus a. So that will be 0 for if the simulation was affine in X. So in that case, you could choose this Lipschitz constant as 0. And so yeah, for linear system, you could pick L equals to 0. And if the system is very nonlinear, the Jacobian will tend to change a lot over different initial conditions, and you would need a large L to satisfy this inequality. Does that make sense? And then you can actually form a proposition. That's one way of discussing how dynamics or simulations of dynamics are more or less nonlinear. So you make some assumptions on the dynamics itself. So that's really your model in some sense, or whatever you use in your ODE. You need some basic assumptions. So you need Lipschitz continuity. That's actually needed for the solution to exist in the first place. For the ODE, you need the sensitivities to be also Lipschitz and also bounded. So essentially that. But these are like very trivial assumptions on your dynamics. But if you have that, then you can conclude stuff about your simulation. So simulating this ODE, one is that the solution started from different initial conditions will diverge according to a limited rate. It's still exponential, so they may diverge exponentially if the system is, for example, unstable, but it's still bounded by this. Also, the derivative of the simulations will be bounded, so that's good news. And most importantly, what we discussed before, the difference between two Jacobians at different points would also be bounded by this thing here. So it, of course, it's related to how far these 2 points are, so linearizing the simulation at different points. But, and that's where I want to go there, it's also bounded with respect to the time. And you can think what happens if t tends to 0, so if you simulate for a very, very short time, well, this term goes to 1, this exponential, so this thing goes to a constant, and this exponential here goes to 1, minus 1, so this thing here goes to 0, okay? So essentially, as t becomes very small, this condition would be bounded by a Lipschitz constant that is very small. So with this kind of construction, you can actually argue that, yes, if I simulate for a very short time, regardless of my dynamics, at least if they have like, if don't have nasty stuff in there, the simulations would become linear if you simulate for a short time, or close to linear. Does it make sense? This kind of things, is it not too hard for people here? Yeah. I don't want to go through the proof. It's a little bit technical and not necessarily fascinating. I just, however, wanted to just to show you some tricks that you would use when you have to discuss these things. If one day you have to play with these kind of questions, essentially relating or saying something about the solution of ODEs in that sense. Huh? If you think about this, what is happening here? I have an ODE that I have no idea about. I just know that it has some basic properties. And then I'm actually concluding things about what would happen if I was simulating that ODE, like bounding solutions and the sensitivities and so on. And that may sound like magic if you don't know the tricks that you can use to do these things. So maybe one thing that can be useful, this kind of inequality. So you can think of A as a vector that moves in time. You think of A of t. And if you differentiate the norm of A, it's actually bounded by the norm of the derivative of A. So you can actually kind of push the derivative inside the norm, and it becomes an inequality. Actually, if you sketch things geometrically, you would see that this is kind of obviously true. But it's a very useful trick when you have to essentially relate the way a norm changes to the way the variable changes inside the norm. That holds for any norm that is almost ever differentiable, like for example the 2 norm or Frobenius and so on. Another trick that is used a lot in this construction is the Grandval lemma. I don't know if anyone has heard it before. Yeah, it's super useful when you have to play with these things. So you would assume that, let's suppose that you can bound this thing here, so can bound how quickly this norm is changing. And you would typically actually use this kind of inequality up here to argue that this bound holds. But if that holds, then you can actually say something about how A over time, or the norm of A over time evolves. And it's related via this fairly nasty stuff. But it turns out that it's essentially, if you can basically bound this alpha and betas, you can unpack completely this expression and end up bounding A of t. And so essentially you can imagine how this is used to argue stuff about nonlinear ODEs. The A dot is essentially your model. That's the F, telling you where the state is going. And if you can bound this thing in some ways, you can basically push this throughout these things, these inequalities, and say something about where the solution A of t is going, as or in relationship to the initial conditions. Yeah, so if you have this kind of questions, oh, I have an ODE and I want to bound something about what the trajectory of that OD is doing, or something around these lines. Remember these things, or at least the names, or at least the slide, and go back into this. It may be that what you're trying to do is not that hard, actually. Okay, using these things, you can do a lot of magic and prove what is in the proposition. So if you're interested, go through that. Okay. Okay, so more of the story, if you don't simulate for a long time your system, you can hope. Oh yeah, we should take a break, I guess. Yeah, okay.